Welcome to my talk about Top-k-Convolution and the quest for near-linear output-sensitive subset sum. My name is Karl Bringmann, and this is joint work with Vasilis Narkos. In the subset sum problem, we're given a set X of n positive integers and the target T. And the task is to decide whether some subset of X sums to exactly T. So for example, if the target is 19 and those are our input numbers, then yes, there exists a subset of X summing to the target. Subset sum is the most fundamental NP-complete problem at the intersection of theoretical computer science, optimization, and operations research. It draws lots of its importance from being a special case of many other problems. So it's a hard special case of the knapsack problem, integer programming, and lots of other problems. And it has applications in modern crypto, because in lattice-based crypto, one of the important problems is called short integer solution, and this is a variant of subset sum. Now, in this talk, we are interested in the pseudopolynomial time algorithms. So in particular, this classic dynamic programming algorithm that is typically taught in undergraduate courses, where you build this huge table T, where the entry I, S denotes whether among the first I numbers you can sum to S. And then by building this huge table, can solve subset sum in time order n times t. And this algorithm is over 70 years old, and over the time people wondered naturally whether this algorithm can be improved. So whether the running time order n times t that we teach in undergraduate courses, whether this is optimal for subset sum. For many years, actually only log factor improvements were known. So for example, on the word RAM, you can shave off a factor of the word size. Until 5 years ago, Kiliaris and Xu came up with the root n factor improvement. And then a bit later, I came up with a near linear time algorithm, O tilde of t times a couple of log factors. And the big difference between those is actually that the classic algorithm and also an algorithm by Kiliaris and Xu, they are deterministic. My algorithm uses randomness, and it's still an open problem whether it can be de-randomized. There were further log factor improvements, but this near linear time in t is the currently best known. Now, they are also matching conditional lower bounds. Assuming the strong exponential time hypothesis from fine-grained complexity, we actually cannot get running time t to the 1 minus epsilon times 2 to the little of n. And there are similar lower bounds from other less standard conjectures, like for set cover and K-clique. So the knowledge that we have on subset sum with respect to parameter t is actually very nice. We have an upper bound of O tilde and t, and a lower bound saying that if you want sublinear dependence on t, then you have to pay an exponential factor in n. Now, today I will talk about output-sensitive algorithms for subset sum. What do I mean by that? So I mean that we are given an instance x and a threshold t, and we want to list all subset sums of x that lie below the threshold t. Or in other words, given x and t, we want to compute this set here as of x and t. These here are all the subset sums of x, and now we are only interested in the ones that lie below t. Now, Bellman actually computes all the attainable subset sums below t in time n times t. That's the classic implementation of it, but with slight adaptations, you can actually get running time n times the output size, so n times the number of distinct subset sums below t. Here I've written this small adaptation, and really it's just Bellman's algorithm, but you store the table in a sparse format where you only store the non-zero entries. Or in other words, what you want to compute in the ith round is all the subset sums of the first I integers below t. How do you get this? Well, subset sum of the first I integers, if it does not include xi, it's a subset sum of the first I minus 1 integers. If it does include xi, it's part of this shifted subsets, shifted set here. You take all the subset sums of the first I minus 1 integers and shift them by xi. If you take the union of those, you get all the subset sums of the first I integers, and we're only interested in the ones below t. Now in each round, the size of a set Si is at most the final output size out. This shifting and taking the union can be implemented in linear time. Basically, this union is like the merge step at merge sort. So the total running time will be order n times out. Now, the natural next question is whether one can get output-sensitive subset sum in near linear time. Near linear and be output size out. Now, 5 years ago, didn't make sense to ask this question because we didn't even know how to shave off this factor n from the n times t. Now we know that this can be shaved off. So naturally, now one can ask whether for this output-sensitive setting, one can also shave off this factor n, which would in some way give the best of both worlds. Like you could shave off the factor n as in the parameter t setting, and you only have running time proportional to the actual attainable subset sums. So it's number out. Now that's the main driving question of this paper, of this research, and it naturally led us to studying a different problem we call output-sensitive capped sumset. So here the input are two sets of integers a and b and the threshold t. The task is to compute the sumset a plus b, and again we're only interested in the ones below the threshold t. And here it is sumset a plus b, it's the natural thing, find the definition down here. You just compute all the pairwise sums of an element in A and an element in B and take the set here, so you throw away duplicates. Now it's standard to solve this capped sumset problem in near linear time in T. For this, you write down the indicator vectors of A and B, and then you compute their convolution using fast Fourier transform in time near linear in T. And the question our setting is whether one can reduce this to near linear in the output size, so in the size of this output set here. And that's actually not so clear. What we do show in this paper, the first main result, is that if you can solve capped sumset in time output size to the alpha, then you can also solve subset sum in time output size to the alpha. Right. The second main result is that capped sumset we can solve in output size to the 4/3. So using this reduction, we also get output size to the 4/3 for subset sum, and this is what we have so far. So there's still a gap between near linear and the output size and what we have. Now this reduction, the first result, it's an adaptation of the algorithm that I presented before. So this near linear and T time algorithm for subset sum. If you add some analysis of how the output size changes in recursive splitting, then you can get this kind of reduction. And I will not talk about the reduction today. What we'll focus on is this algorithm for capped sumset. Because this is also more interesting from the technical point of view, because additive combinatorics comes into play. Now, let me give you a bit more motivation why we're interested in this capped sumset problem. I mean, I already gave you a motivation from output-sensitive subset sum, but there are actually more related problems that are interesting here. Namely, the algorithm that we design, it also solves a couple of other problems in a similar running time, k to the 4/3. First problem is top-k sumset. So here we have two sets of integers a and b. We want to compute the k smallest or the k largest element of their sumset a plus b. So this is natural top-k variation of this problem. A bit more general is Top-k-Convolution. So here we have two sparse non-negative vectors, and what we want to compute is the k leftmost non-zero entries of their convolution. Now this is one of the problems mentioned in the title of this paper. It's actually equivalent to this top-k polynomial multiplication, where you're given two sparse polynomials with non-negative coefficients. And what you're interested in is to compute the k highest degree monomials of their product. Or equivalently, you can also ask for the k lowest degree monomials of their product. Now, this really is a very natural problem. We often encode things in polynomials, so computing the k highest degree monomials is a natural application. And to the best of our knowledge, this specific formulation of the problem has not been studied before. And we are the first to design this k to the 4/3 time algorithm for this. Right, so this Top-k polynomial multiplication and Top-k-Convolution, they're basically equivalent. And Top-k Sumset and kept Sumset, they're also basically equivalent. But the Top-k-Convolution is a bit more general, but our algorithms can be expanded to this setting. Okay, that was a bit more motivation for kept Sumset. Now let's go to algorithms for this problem. So recall I want to compute a plus b intersect t. So I kept the Sumset at t. We write out for the output size. Now we always have these inequalities here, that the size of a and b is at most the output size is at most size of Sumset, and the Sumset is at most size of a times b. Now this inequality here is immediate from the definition of the Sumset. This inequality here is immediate because we want to compute a subset of the whole Sumset. The first inequality, for this you actually have to do some without loss of generality reduction. Namely, we remove any element of A such that if we add it to the minimum of B, we're already larger than T. Then clearly this element of A is irrelevant for the problem, and we can remove it. If we do a similar thing for B, then we can guarantee this inequality. Now we will use these inequalities throughout. You can actually check that these inequalities, they can all be tight. They can all be also very far from tight, meaning that one number is n and the other is n squared. There are easy examples that show that all of these inequalities can be tight and very far from tight. So if you're interested, you can pause here and check out the examples. I will not discuss them now. Okay, so we will make use of these inequalities. Let's first analyze the naive algorithm. So naively, we can just compute the Sumset a plus b by enumerating all pairs of an element in A and an element in B. And then we collect all these sums, throw away the ones that are above T, and we get the kept Sumset. Now this runs in time size of A times size of B, which using this inequality here is at most out squared. Now what I will show you next is first a baseline approach that solves the problem in output size to the 1.5, and then a proof of concept algorithm that includes some additive combinatorics and shows that this can be used to further reduce the rank time to output size to the 1.4. The actual result that we have in the paper is output size to the 4/3, but I will not go into details of this here. Now, throughout the discussion, I will have this picture here where I have this set A sorted from smallest to highest, set B sorted from smallest to highest, and a pair of element A and element B is marked green if their sum is below T and red if the sum is above T. And then note that out is, well, what we want to compute are all the distinct sums in this green region here. So the output size is the number of distinct green sums. Basically, the bad situation is that there are lots of distinct red sums. Okay, let's start with the baseline algorithm. So for this, we will use this ingredient number 1 here, namely that some sets can be computed in near linear output sensitive time. A plus B can be computed in time near linear in size of A plus B. This is which are a relatively old algorithm from due to Cole and Harry Heron. Now, the first urge here would, of course, be to try to open up this algorithm and try to adapt it to the setting of kept Sumset. Tried that, it didn't seem to work. So what we are doing right now is to use this algorithm as a black box. Okay, what do? We split A and B into G groups. So those are the groups in B and groups in A. This gives rise of pairs of groups, these boxes here. And I'm marking a box green if all, all the sums within the block are below T, I'm marking a box red if all the sums are above t, and yellow if some are below and some are above t. Now what we do is we iterate over all the green and yellow boxes, all the boxes that have some pair summing to at most t. For each such green or yellow box, we just compute the sumset ai plus bj. So just all the distinct sums within a block. And we do this using this ingredient one, this Coland-Hariharan algorithm. Once we have this, we throw away everything above t and we add it to the output. Very simple algorithm. Just iterate over all the green and yellow boxes and compute their sumsets using ingredient one. What's the algorithm of this baseline algorithm? First of all, if you look at one green box, then it's contained in the green region. So this sumset ai plus bj has size at most out. Not only that, if you look at the whole diagonal of green boxes, then well, all the sums in here are below all the sums in here, so they are distinct from each other. So even the total output size along a diagonal is upper bounded by the output size. Because we have basically g many diagonals, 2 times g, output size for the green boxes in total can be bounded by g times out. Now for the yellow boxes, we cannot bound anything in terms of the output size because some of these sums are above t, are not counted in out. So what we instead do is we upper bound the sumset size by the trivial bound. It's at most the product of size of A times size of B. And because we split into G groups, what we get is that it's at most size of A times size of B over G squared. And because the boundary has size order G, what we get is running time A times B, size of A times size of B over G. So we have these two running times. If we balance these two by appropriately setting G, what we get as running time is square root of size of A times size of B times output size. And because size of A and size of B are at most out, this running time is output size to the 1.5. And well, I'm slightly cheating here because said that we pick the right G, but this actually depends on out. So what you should actually do is to run this algorithm in parallel for log n different values of G. Now that's the baseline algorithm. It actually turns out that there are sets of numbers where this green bound here is tight. There are also sets of numbers where the yellow bound is tight, but we could not find any sets of numbers where they're both tied together. And this seems to be due to some restrictions on some sets of numbers, restrictions of a form that are studied in the field of additive combinatorics. Right, so one of these restrictions is called Ruja's triangle inequality, which says that for any sets of numbers a, b, c, the size of a plus b is upper bounded by the size of a times a plus c times the size of c plus b over the size of c. Now, what does this tell us in our situation? Claim that it gives this easy corollary here. So this is looking at the smallest x numbers in A and all the numbers in B. So let's assume that all these numbers are green, all these sums are below t. And let's suppose the same holds for set A and the y smallest numbers in B. Then what the lemma says is that the whole sumset A plus B, so all the green and red sums, the number of distinct such sums is bounded by out to the 3 over x times O. So given knowledge about the sums, about the green sums, the sums below t, we gain knowledge about the red sums, the ones above t. It's very useful in our situation. To claim that it follows very easily from Ruja's triangle inequality. What you do is to apply it once. First you introduce the set b at most y, then you apply it again on this term here and introduce the set a at most x. What you get is this here, where the numerator contains a plus by as a product, then by plus ax, and then ax plus by, ax plus b. All of these three terms are within the green region, so they're all bounded by the output size out. So the numerator here is out cubed, and the denominator is x times y, so immediately get this lemma. Now let's use this structural insight from additive combinatorics to give a proof of concept algorithm that actually these structural insights can be used to improve the baseline algorithm. What we do is we split the problem into three subproblems. We define x and y to be slightly sublinear in the output size, out to the 1 minus epsilon. And then we look at the subproblem a and the smallest y numbers in b and the smallest x numbers in a. And then there can be a little bit of green region left here, and we cover it by the smallest rectangle. So some rectangle between the origin and covering all the remaining green elements. Those are the three subproblems that we solve. First two subproblems we solve using the baseline algorithm. We call it the baseline algorithm runs in time square root size of a times size of b times out. Now, in the first call, the size of b is smaller than out. The second call, the size of a is smaller than out. So what we get is actually a polynomial improvement over the out to the 1.5 running time from before. Now, for the third call, we just run the first ingredient, so this Combinatorics algorithm. So we compute the sumset in time near linear in its output size. And we bound output size using the lemma from structural lemma from before. Obviously, because we know that all of this here is green, and we know that all of this here is green, so this lemma is applicable, tells us that this output size is at most out cubed over x times y. And the way we chose x and y, this is again better than out to the 1.5. Choosing the optimal epsilon here, what we get is output size to the 1.4. Now, the baseline algorithm was output size to the 1.5. It gave you this proof of concept that it's output size to the 1.4. In the paper, we actually show this output size to the 4/3. So this is a bit more elaborate use of Foucault's triangle inequality, where we have like a set of active subproblems, and then have a coarse to fine-grained approach where we split these active subproblems into smaller and smaller, and at no point in time there can be too many active subproblems. Now, let me discuss, and the same then also gives, right. And then we also get an output size of the 4/3 algorithm for subsets via this reduction that I mentioned before. Now for this capped sumset, we had an upper bound, a threshold t, and we're only interested in these sums below t. Now if we also introduce a lower bound, then we get what we call interval restricted sumset. For this, the same baseline approach works. And we still get this running time square root size of a times size of a times out. And we show actually a conditional lower bound that this running time should be close to optimal. Meaning that for this capped sumset, where we only have an upper bound, the structural insights that we use to get proved algorithm, it actually uses the fact that we only have an upper bound and not also a lower bound. We also more generally study algorithms that build on rectangle coverings. So all the algorithms that you design in the paper are of the form that you look at boxes or rectangles. So you have some consecutive elements in A, some consecutive elements in B, and you have they span some box, and inside this box you use the ingredient one, this Combinatorics algorithm. Any algorithm that performs this kind of rectangle covering must have superlinear running time, at least output size to the 1.04. This is what we show. Unfortunately, it's all really a result about a restricted class of algorithms. It's not a conditional lower bound. So it's still open whether capped sumset and subset sum, whether they can be solved in near linear output sensitive time, or whether we can find a superlinear conditional lower bound. We also don't know whether the approach that we have using coverings, whether this is universal, whether any algorithm can be written in this way, or whether there are very different kinds of algorithms. Let me finish with this one open problem here. So we looked into the direction of minimizing the exponent of out. You can also look at the other way around, trying to start from this n times out running time and reduce the exponent of n. So you can ask whether there is an n to the 0.99 times out algorithm. And this is actually open. We do not know how to get this right. Okay, let me stop here and thank you for your attention.